Welcome to homework.
All right, we've got a 1,2-dimethyl cyclohexane, and it is the trans conformer. Sorry, the trans configuration. And so we need to look at the chair to determine what our lowest energy conformation is. So we'll draw the chair, and then we'll draw the ring flip of the chair. I like to draw my cyclohexane chairs. It's a series of connected parallel lines. All right. Then I like to go to my overhead view and number things so I can just keep everything straight. That's a 1, that's a 2. And then I like to add just the bonds that will be relevant, such as I know that 1 is going to have an axial straight up as well as an equatorial. And I know that 2 is going to have an axial straight down as well as its equatorial. And I know that the relationship between the methyls on carbons 1 and 2 are that they're on opposite sides of the ring. So if I draw my methyl up here, and recall that, drawing this either way would be valid. Just because it's above the ring here doesn't mean it has to be above the ring here. I could always flip this around and draw it that way, just to avoid any confusion. I'm not drawing the methyl axial because this particular methyl group is pointing up. That's not necessarily the case. It happens to be the case this time. Okay, so I've drawn my methyl group up, which means it's the higher of these two, right, between the methyl and the hydrogen. And then for my other carbon 2, if I've drawn the methyl as the higher of the two on 1, then I know my methyl on 2 has to be the opposite, has to be the lower of the two. So it's axial down. And we've got a hydrogen there. And now I need to draw the ring flip conformer. So I start with parallel lines in the opposite direction, draw 2 more parallel lines, and then I connect my sets of parallel lines. Okay, and when I draw this ring flip conformer, if I call this carbon 1, the upper right-hand carbon, I call the lower right-hand carbon 1 as well, and then I call this carbon 2. Okay, so let me add the bonds. I know I'm going to have axial down for carbon 1 and equatorial up and to the right. And for carbon 2, I'm going to have axial up and equatorial down and to the right. Now I know on carbon 1, if I want to stay consistent, methyl's got to be the higher of the two, hydrogen the lower of the two, whereas on carbon 2, methyl should be the lower of the two, and hydrogen the higher of the two. And now I've got to determine the lowest energy conformation. So between these two, related through a ring flip, which is lower energy? Well, I know for a fact that methyl groups are lower energy when they're equatorial and higher energy when they're axial. So if I've got any sort of functional group sticking off this ring, they're going to be big and bulky. I'd prefer the version that has the bulkier things equatorial, or that just has more things equatorial. So everything's equatorial over here. That's lower energy. That's the most stable. This is the lowest energy conformation. Okay, let's move on to the next problem, and we can go a little quicker this time. I won't have to explain so much about the chairs. Okay, so we've got a wedge to methyl and a wedge to an isobutyl. So let's start with my chair like this. Okay, carbon 1, carbon 2. Got to have an axial and equatorial substituent. Got to have an axial and equatorial substituent. I'm arbitrarily picking methyl to be the upper of the two, which means hydrogen has to be the lower of the two. And on carbon 2, I know that my isobutyl is going to match my methyl. My methyl's the higher of the two, so the isobutyl should be the higher of the two. Right? And that makes hydrogen the lower of the two. Okay, and then the ring flip conformer. This is carbon 1, this is carbon 2. Scroll down just a tad to give myself some room. Connect that. Okay, so on carbon 1, I know I have to have an axial down substituent and an equatorial up and to the right. And on carbon 2, I need axial up and equatorial down and to the right. On carbon 1, I know methyl should be the higher of the two, and hydrogen should be below. And on carbon 2, I know isobutyl should be the higher of the two, and hydrogen down below. So now what I've got to compare is a methyl that is axial to an isobutyl that is axial. Basically, the thing that's equatorial won't make too much difference on the energy. So the question is, would I rather have a methyl axial or would I rather have an isobutyl axial? Well, recall that isobutyl is much bigger than a methyl. It's almost 3 times as big, right? It's got a carbon here, a carbon here, carbon here, and then hydrogen sticking off those carbons in addition to an additional hydrogen here, whereas the methyl just has 3 hydrogens. So isobutyls are bigger and bulkier, and therefore are much preferable to be equatorial, where they could be out and far away from the other axial groups. These hydrogens across here, right? The 1,3 diaxial or the flagpole interactions are what we're trying to avoid. So the more stable conformation is the one that puts isobutyl equatorial.